You are an industrial engineer with a shipping company. As part of the package handling system, a small box with mass 1.6 kilograms is placed against a light spring that is compressed 0.280 meters. Okay, let's draw this. So we have a nice box right here. That's not a box. I don't know what that is. Okay, that's better. And there's a spring that the box is against. Now there is a force that pushes the box towards the spring, and what happens is the spring compresses by 0.28 meters. Now once this force stops compressing the box and the spring is released and the box has a velocity going this way. Okay. So what else? The spring has a force constant K equals 45 newtons per meter. The spring and box are released from rest, and the box travels against a horizontal surface for which the coefficient of friction with the box is mu K equals 0.3. So now what the question is saying is that as the box slides this way, there's going to be a force that's opposing its motion, okay, and that's the force of friction. Okay. Now when the box has traveled 0.280 meters and the spring has reached its equilibrium length, the box loses contact with the spring. A, what is the speed of the box at the instant when it leaves the spring? Okay. So here, I denoted 1 as when the spring is compressed and 2 as when the spring is released and the box is moving. Okay, that's just for your context, your context when I'm forming the equation. Okay, so in a situation like this, we know that we're going to have to use energy, and we also know that there's a non-conservative force, friction, at play here, which tells us that we can't just say energy before equals energy after. Okay, we need to factor in the work done by friction. Okay, now the work done by any non-conservative force is equal to the change in potential energy plus the change in kinetic energy. Okay, now in this case, the potential energy comes from the spring, because when the spring is compressed, it's storing the potential energy that gets converted into the kinetic energy when the box is moving. Okay, so let's see. The work done by friction is going to be equal to the force of friction times the distance friction's experienced, cos 180, and I'll explain that in just a sec. And the change in potential energy would be PE2 minus PE1 plus KE2 minus KE1. And remember, 2 and the 1, they come from here, okay? So the reason why I included cos 180 is because of this. So the box is moving this way, but friction is acting 180 degrees the opposite way. Okay, let me draw that here. Okay, so the velocity vector of the box points this way. Okay, and then there's 180 degrees between the friction vector. Okay, and that's where we get this cos 180. Now cos 180 is equal to -1. So here there's going to be a negative sign in front of this term. Okay. All right. So here, let me get rid of that. Okay. Now let's think about what it means when the box is at rest. So when the box is at rest, okay, V1 equals 0, which means that there's no kinetic energy at 1. Okay, so we can get rid of that term. Now when the box is moving and the spring is fully released, there's no more potential energy on the spring because the spring has already converted all of its potential energy into kinetic energy. So PE2 is going to be 0. So we can rewrite this and say KE2 minus PE1. Okay? Now we need to write in our equation for spring energy and kinetic energy. And that's going to be mv2 squared over 2 minus kx squared over 2. Now for friction is equal to mu k, in this case kinetic friction, so it's going to be the coefficient of kinetic friction, times Fn. Okay, now in this situation, the box is not moving in the vertical at all. Okay, so it's only sliding against a surface going this way. So in this situation, the force of gravity would be equal to Fn. So we can say that mu k mg, oh sorry, there should be a negative there. Okay, oh my goodness, that's not, there we go. Okay, so now we have all of our variables established, and all that's left to do is isolate for V2 squared, okay, or V2. So I'm going to do that, and I'll come back once that's done. Okay, now it is time for part B. What is the maximum speed of the box during its motion? Okay, so a few things you need to recall for this question. The first one is that the derivative of velocity equals acceleration, okay? Now, the second thing you need to remember, I will explain it using a hypothetical graph of velocity. Now, let's say this is a graph of velocity with respect to time. If I were to ask you, at what point is the velocity at its max, okay? Or in other words, when is this object at its fastest? You would say right here, okay? Now, if you were to take derivative of this graph, it would be a line like this. And recall that the max and mins of a graph, or any area on a graph where the horizontal tangent is 0, that point will become a 0 of the derivative function. So in other words, when acceleration equals 0, we have a max velocity. So to solve part B, what we need to do is figure out an equation for acceleration, which is going to be a at x equals f net of x divided by m. Okay, that comes from Newton's second law. And what we're going to do is set acceleration. We're going to set this equal to 0. And before we can solve for our max velocity, we're going to solve for the position x at which the max velocity occurs, okay? So let's see here. A at x we're going to set equal to 0 equals f net of x over m. Okay. Now we're going to expand our f net equation and figure out what forces are acting in the x. So, okay, so let's see here. if the box is moving this way and friction opposes motion, friction is going to be acting in this direction. And the spring force, okay, the spring force is the force that pushed the box outwards, is going to be acting this way, okay? And we're going to say that the right is positive x and the left is negative x. So in that case, if we have the spring force directed towards the right, it's going to be positive minus the force of kinetic friction, which is directed to the left. Now what we can do is just multiply that m by the 0, and we have force of spring, okay, or yeah, the force that comes from the spring minus kinetic friction. Okay, so now what we need to do is get in some variables into here. So the force of the spring equals k times x, and the force from kinetic friction is mu k Fn. Now we said previously that because the box is not moving in the vertical, Fn is just equal to mg. Okay. Now we just need to solve for this x, which I will come back and show you. Okay, so after solving this for x, you should get x equals 0.104 meters. Okay, so now what we need to do is rewrite our energy equation. Let me just take this and copy it over here. Okay, so same story as before. Work done by a non-conservative force equals the change in potential energy plus the change in kinetic energy. Okay, now we know what the work done by friction is. Okay, from the same question, that hasn't changed. Now we know that the change in potential energy is PE2 minus PE1 plus KE2 minus KE1. Okay, so this question is a bit different because I've denoted 1 and 2 differently than I did in part A. So 1 is when the box is at rest and compressed by 0.28 meters. So if the box is at rest at 1, then KE1, kinetic energy at 1, is 0. Okay, now at 2, the box experiences a max speed at 0.104 meters. So at 0.104 meters, the box is still in contact with the spring. So we still have potential energy at 1, which is why that's not equal to 0. Okay, just in case you were confused by that. So we can rewrite this equation again and put in some more variables. So potential energy at 1 would be, at 2 would be k times x at 2 squared. Okay, minus k times x at 1 squared plus mv max squared over 2. Okay, so now what we need to do is rearrange this equation and solve for Vmax. Now, let me do that real quick. Okay, so after solving for everything, you should get that the maximum speed of the box is 0.93 meters per second. I ran out of room here, so I just did it on another page. But yeah, thank you for watching.